All right, so I got all of these ingredients. They are amazing. They taste so good. I got sauce and oregano and flour and yeast and cheese and a pan and basil, I believe. I'm not going to tell you the, well, I did tell you the amount, so no, you can make it too. All right, so how does this work? In chemistry, we take ingredients, which we call reactants. So what we do is we mix them all together. And it makes a beautiful pie, which is our product. And that's what happens. So let's talk about how that's going to work for us. All right, so this is how it makes my delicious pizza from Pizza King, where I've been working since I was a junior in high school. Pizza King. And this is what's in the back warehouse. I broke in last night. I looked. I still know the code. All right, so on your sheet, there's a little box on the right, and it's going to help a lot. First off, cross out water. I believe there's water in there, I think. Is there or not? In the box? All right, oh, in the directions. Don't worry about that in the directions then. So, let me show you how this is done. I don't need to see a lot of work. I just need to see some answers, and it will help relate a complicated idea and make it real simple. If I had one pizza making one pizza pan each time, and I have 510 pizza pans, how many pizzas can I make from the pizza pans? 510. So what you do is you would just put a slash under the 510, put a 1 equals 510 in the box. So you can do that in the box. I will do one more with you, and then you'll do the rest. 63,000 kilograms of sauce, and each pizza needs 120 grams of sauce. So what you could do, first, just make sure we understand the difference. How many grams is 63 kilograms? 63, 100 or 1,000? Kilo means 1,000, so it's 63,000. So I would take 63,000 slash 120 equals, and then I get how many pizzas I make with that. Okay? So what I want is 6 more numbers, counting that one. So you just put a little slash of how many there are. Put a little slash right there, 120, hit equals, and put an equals, and then with your calculator, put 63,000 divided by 120. So write all the different pizzas. This will help. The entire conversation today is about the pizzas. So it would be beneficial. It's also on the sheet. Work. Oh, already? Oh, then you are enjoying good dancing. So we should be finishing up. Just the number. You don't need to show much work. We're just taking that. So for like the next one, you take 100,000 and divide it by 250. And then I'll tell you how many pizzas that one would make. Okay, all the kilos are thousands. You want to answer then the questions on the top? That would help a lot. But we're going to kind of talk about it as we go.
Mi farò prestare un soldino di sole perché regalare lo voglio a te. Potrai posare sui biondi capelli quella nube d'oro accarezze. Questa ultima sera con un voce si può cantare. Ogni innamorato all'innamorato.
All right, so let's talk about it. We should be kind of finishing up. All right, so I take all these ingredients and I want to make my pizza. But how many can I make from each? So we already had that first one. Pizza pans was 510. How much for the sauce? 525. So you take with 62,000, you divide it by 120, you get 525 pizzas. And so on and so forth. Cheese would be, hopefully these are your numbers, 400. The basil would be 625. Think that's flour, 750. Yeast, 500, or vice versa. They look very close. And the oregano. Then I put the pictures in the wrong spots. Well, so you did not know that, because you haven't been cooking as long as I have. All right, so what does it all mean, and where does it all go? If I had those ingredients, that's how many pizzas I could make from each one. Let me tell you a story, true story. I'm just a wee chef. I'm 17 years old, and I'm working at the best pizza and sub place in Appleton, Pizza King, and free advertising. And a guy calls and says, we would like a pepperoni pizza. I'm like, I'd love to make you a pepperoni pie. And he's like, with no cheese. I'm like, oh, lactose intolerant. That's too bad, but good for you. So I'm going to take the cheese off. And he goes, and no sauce. I go, so what's on the pizza? It's like, just do the crust and put some pepperoni on there. I'm like, I'm getting punked. So I'm like, okay, fine, I will make that. So I get the crust out, I put the pepperoni on, I put it in the oven, I take it out, and all the pepperonis are all curled up into little burned up little sausages, looks like little hot dogs. And I go to cut it, and as I'm cutting it, all the pepperoni falls to one side because they're not stuck to anything. So I just have loose pepperoni pieces all on just a burnt crust. I'm like, all right, this is not going to go well. The guy comes in, he opens it up, and he goes, perfect. I'm like, what? So that's the way he liked to eat his pie. Never came back. I was afraid of making it again. He never came back. All right, so this is the key thing on the bottom. What we talked about, and I put it on the top of the sheet just out of respect for Blue Lightning and Black Mamba. We talked about limiting and excess the other day. So these are the big words in cooking whenever we are working with anything like that, and cooking is chemistry. So a limiting reactant is a reactant that is consumed in the reaction. It is very important that we understand that. The excess reactant is the reactant that is left over. So it's unreacted. And these words will show up. We don't have many vocab words, so when we do, they're probably pretty important. So we have limiting reactants and we have excess reactants. All right, so let's take a look. We're not doing a lot today. We're doing some examples. We'll give you a little bit of time. We'll talk about the rest of the week. Give you about 20 seconds more. Is it hot in here? Is it me? All right, so I have a real simple demo. You probably did this back in elementary school. But for some of you, I just invited your Dark Lord, and you are very happy right now. So there you go. So this might be the best part of your whole day. Like, oh, he's back. Or she. If whenever light shows up and you hear this, you need to go seek help. It's just a thing. It's just a thing. All right. So what happens is a candle, wax, is actually called paraffin. And it's okay. It's basically hydrocarbons, carbons and hydrogens. There's no formula because there's all sorts of different kinds of formulas that all exist in there. But when we light it, it reacts with oxygen and it makes CO2 and H2O. So it looks like this. Literally. The oxygen and the candle, the wax, let's just call it the wax, that goes in together and it creates that flame, and what comes off is H2O and CO2. So, right now, what reactant runs out first? What's going to limit my reaction? Eventually, reactions always end. What's going to run out? The wax or the oxygen?
The wax.
Hopefully the wax, or we're in a lot of trouble. We're all going to die. And this will be the last voice you hear. Which I'm sorry. But it is what it is. The wax is going to run out. There's unlimited oxygen. But, so there you go. There's my box. Now I'm showing. But let's get creative. Obviously, this is not very fancy, but it does the point, does the trick. And I'm putting that there because there's a hole on this side. Oh, look at that! I'm covering it up. I don't know what accent that is. So which one will run out now? Well, clearly, hopefully, if it ever happens, the oxygen will run out. And if you look really carefully, it runs out right there. It ran out. And that's absolutely awesome. That's chemistry. That's like cooking. Right? So we run out of the oxygen. Hey, look, the candle's still there, but there's no fire. So it must have been the oxygen. It was all used up in that beaker. All right, I got another one. They're all backfiring today. That's okay. I'm a chef. I'm not a chemist. I don't know which one's which. Okay, so I have 3 Erlenmeyer flasks. They're all pink right now, and why they're pink is that they have hydrochloric acid in them. And hydrochloric acid is not pink, but I put this really magical solution called universal indicator, and when that goes into an acid, it turns red. So the red is proving there's an acid there, okay? What I'm going to do, the numbers mean nothing. What is limiting, what is excess? And remember, we're going to have some fun with this later. Actually, we'll do it right in the middle. We'll do one early and one late. So here we go. Problem is, it's hard to get them out of the blue. You can do it. Uh-oh. Uh-oh. It's going to block it. We're really cooking now! Oh, I've been waiting to use that. So exciting. I'm a little worried about this one. I don't know what that is. You go back up there. All right, so let's take just a second. This took a lot longer than I wanted to last hour, but... Oh! Ooh. Fancy. And as we keep going, you can tell that this one, I don't know why I'm using a laser pointer, is very dark pink yet. Very dark pink. So what it's saying is that there's a lot of left over, and I flipped this. Let's just show everything now. I have a lot of excess HCl because it's very dark pink. I did not use a lot of zinc. And what you can tell is I'm not going to make a lot. It's like cheese. And once I run out of cheese, I'm running out of pizza. I don't know if that's Italian. I'm just going to keep going. So, by the way, did you know on YouTube you can research how to speak in different accents? But somebody didn't have enough time to watch enough of them last night. So, but that's all on YouTube. So it's actually kind of cool. Then you can see, based on these other two, the balloons are about the same size, but this one has a little bit of pink, and this one looks, maybe I'm seeing it wrong, like the pink's basically gone all the way. So because the HCl was all consumed, or it's going to be, that the HCl was the limiting. It's going to limit that. So this one was, the goal was to have a perfect reaction between the two, which would make the most product, because both of them are going to be used up, and I don't have any excess. The thing is, I got to keep it reacting for quite a long time to see if it's actually going to use it all up. But like, for example, this one was this one last hour, and there was no zinc left whatsoever. So again, that's like this. Like, I ran out of zinc. It's gone. It's not there anymore. Unfortunately, again, the acid takes a while. When this is all done, we'll blow these up. All right, so some hours, what was it, a couple of months ago, we had some challenges. Believe me, no challenges. These blow up loud. Mr. Sperduto said he could feel it, and he was sitting at his desk. I don't know what that means, but we're going to go with it. That's pretty cool. So, all right, here we go. So, you said that Pizza Pan's made 510 pizzas, and you said that she's made 400 pizzas. So, you should have a problem. Is it on the back? I don't know where I put it. Is that where it is? All right, here we go. Do this with me, please. It basically says, how many grams of magnesium chloride will be produced when 50 grams of hydrochloric acid reacts with 20 grams of magnesium? So, what we do, like always, and what we've been trying to make you do, is organize your information. So it says that I have 50 grams of HCl. I have 20 grams of magnesium. How many grams of H2 would be made? Okay? Even if you don't know how to do it yet, we write down what we know. Because there's basically multiple different kinds of problems that we're going to be doing stoichiometry with, and you need to know. So now, if you're in the party that, hey, I never figured out T-charts yet, you still got another shot, okay? So, let me ask, If I ask how many pizzas you make, you said, okay, with the pan I made that. All right, then how many pizzas can you make just with the cheese? Well, what about if I do the same thing? What if I have this much acid, how much of that am I going to make? If I have this much magnesium, how much of that am I going to make? So what I want you to do is make 2 T-charts above and below each other. And if you're like, man, now I got to do twice the work, it's not fully twice. It's about 1.5. I'll meet you in the middle. All right, so I'm going to do this first one with you quite a bit. You're going to kind of work on the next one by yourself. So what I'm doing, please keep this straight. You have 3 things, correct. But what I'm trying to find is 1 ingredient to the final product. 1 ingredient to the final product. So how much HCl, or the amount of HCl makes how much hydrogen. So here we go. Grams to grams. So I bring the molar mass down. 35.45 plus 1 is 36.45. What goes on top? Moles. I'm going down to moles. You should see this flow chart. Then, the flow chart, what do we see next? I see mole ratio. So I look at the actual balance equation. There's a 2 in front of HCl, so that's why it's 2 moles HCl. What's in front of the H2? There's 1. So it's 1 mole H2. And now I'm going to grams. So I hope that you kind of see that final part. I'm going back up to grams. Again, I'm going through the flow chart. It doesn't change. The thing that changes, molar masses. All right, so then I go down. That's like saying, hey, I have that many pans. How many pizzas? Well, that's how many pizzas. Well, in this case, that's how many grams of H2 I'll make. 1.37 grams of H2. But I also have cheese. And how many pizzas can I make with the cheese? So I'm going to do the exact same idea, finding, and this is the key thing, I'm finding the same final thing. So check this out. This, and this should be exactly the same from the previous one. I just literally take them and bring them down. First part will be a little different. First part will look like that because it's a new beginning compound, but the ending's exactly the same. And I want you to be able to recognize that. And then I got 1.65 grams of H2. Don't know. I had to make an AP video last year. Once my daughter was sick in the middle of the night, I came in and I was so loopy. I thought it was a Louisiana Bayou accent. I did the whole video for 18 minutes in a Louisiana Bayou accent, but they disagreed. They thought it sounded like a pirate. So anyway, all right. So how many pizzas can I make? I hope we agree it'll only be 400, right? You're not going to make, except for the guy who only wants the pepperoni. If I make the same pizza every time, I can only make 400. Well, which one, how much H2 can I make then? I can make the smallest amount. And that's what needs to be registered right now. That's why we did the pizzas. You can only make as much as your ingredients allow. So if I can only make 400 pizzas from cheese, I'm never going to get to 510. This one makes 1.65 grams of H2, but the reaction is going to stop right here because this is going to run out. Now, I did not write this in the last hour, and I'd like you to write this right here. Put an arrow to the HCl. That is limiting. Please say limiting. And the Mg is excess. We don't write it at the end, because the end is the final answer. When we ask what is the limiting or the excess reactant, it's the reactants or the ingredients, going in and out of accents here, that you start with. So this is the limiting. The one that you boxed, the beginning part was your limiting reactant. The one that's not boxed is your excess reactant. And the excess never dictates how much you make. It's only the limiting. So, what I'd like you to do is I'd like you to start the next one on your own. We only have one more big one to do. I will do one with you on your homework as well. But let's start that one, please. So, how many grams of nitrogen are produced if 18.1 grams of ammonia reacts with 90.4 grams of CuO? You organize your information. Anybody seen Madagascar 3? They're in the circus. I feel like I'm talking like the seal. You know? So, that will get you started.
non ti sento da sti braccia, non ti rasi questa faccia, non ti stringe forte un braccio a me. Ma scendere ma si suona, ma fa chiagnare a volta. Si sta morendo sta contenta, non pensa sola, non siamo sopra, pensi solamente a me. Ah, più belle tutte belle,
Do you have a problem getting started? You got to bring the unit down. Mirror what the other problems are like. When you're going down the grams, you're going on mole ratio, then back up the gram. All right, so we got to get used to it. It's repetitive. There's no reason that we can't be strong at this. Oh, what's that? Get up. So the mole ratio for the first one would be a 2 on the bottom and a 1 on the top. Right, and then I find 28 1. So the minute I figure it out, the second half of my problem is exactly the same. Exactly. Again, if you're doing this, you got to be honest with yourself. There's no reason that we shouldn't be able to start filling in these T-charts. The more we can fill in each time, it's a little bit more of a success because it's the same concept every time. Every time. It's just how do we apply to different situations, like today. So the other one, this will be the beginning part. And this time there's a 3. 3, 3, 3. There's a. Be a 1. And that will give me 10.6.
How many decimals do you want? How many decimals?
Usually 1 or 2 tops. Like this, because there's 1 at the end, you can kind of leave 1.
Oh, yeah.
And then what do? Do I add them? Take the biggest, subtract them, take the smallest. Those are all options I see on tests. I'm going to what? Take the smallest. So there's my answer. Okay? I can only make that much. If you're like, well, no, well, each one makes that. You got to remember, these are reacting together. Pizzas and pans and cheese, we're putting them together to make pizzas. One of them's going to run out. Once it runs out, the pizzas are done. All right, so we always take the smallest answer. All right. So 10.6 would be what I choose, not 14.9. Again, don't subtract. All right, we have one more little thing to talk about, which we will relate later in our lab coming up, which is a very fun lab, and then what's happening the following week. So, percent yield. Yield, for many of you, what it means is that you slow down a little, you look both ways, and then you hit the gas. Yeah, I've seen you drive, I know. But in chemistry, yield is to produce or to create. When something's yielded, you're making it. Okay, so this is important. Kind of write it to the left because I'm writing stuff on the right over here. Let's say you're playing basketball or you're doing anything. It doesn't matter. You're throwing passes in a football scrimmage, or you're shooting free throws or whatever. The amount actual versus theoretical relates to that. It's whatever you're doing. You're taking 10 free throws, let's say. That's how many you're actually doing that's how many you should make. But the actual is what you actually did. So, the actual yield, what is actually made. So if you went out and shot 10 free throws and you only made 6, well then your actual yield is 6. And that's the real lab amount. That's what you actually did. That's the real, and this, people get this confused, so hopefully you do label this, because this, you might have to come back to this. It does happen. The theoretical is what you hear. Sometimes people will say something like, well, in theory, so you're saying like in a perfect world. Well, in a perfect world, yeah, these numbers will happen a certain way. This is what should be made. And that's stoichiometry. I cannot emphasize this enough. Everybody who does a percent yield problem, if you're stuck, what you're doing is like, I don't know what to do. You need to do a T-chart. You might even want to write T-chart to find that every time. You are always finding that bottom number. And we're going to practice it once, but you are always finding the bottom numbers. So, give you a second more to write. We're going to do one problem. All right. So, soon enough, it's getting warm outside. You're going to be grilling in your backyard maybe, or on your deck, or something like that. Got a propane tank. So, if 50 grams of propane reacts and produces 75 grams of water, what is the percent yield? First, if you look at a problem and go, I don't know what propane is, you need to think a little. Like, that's oxygen, that's carbon dioxide, that's water. So, processed by elimination, ding, 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 that's probably propane. So, we organize our information. Please write down where these numbers go. Just where they are, where are they? You may not know them all, but you can at least put those 2. Again, you may not know how to do a problem until you start. But once you start, you've organized it, then it tells you how to do it, basically. So, I'll show you. The 50 is the propane, 75 is the water. That's all it says. Now, the fact that it says percent yield, that means that I'm going to be doing this eventually. But that's not it right away. I need to always find that. So, this is the secret trick. What people get confused about is they say, well, I don't know what I'm finding. There's no question. The question is what's produced. It's saying that it made 75 grams, but let's find out how much it should have made. Okay? So, in combustion, when you react, I don't think I said it this hour yet, when you light this candle, it's yellow or orange. It's an incomplete combustion. If I put something on top of it now, it's going to start getting black because it'll get carbon soot. I don't see carbon as one of my products. So this is an incomplete combustion. It's not very efficient. Okay, when you see a Bunsen burner on your grill and it's blue, it's burning and it's reacting with the oxygen at a much higher rate, a better percent yield than that candle. So what I need to do is I need to find GH2O still. And that's what's confusing. Wait, you already have it. That's what was made. What should I have made? So here we go. I put 44 grams of C3H8 on the bottom. You should be able to do this. You go in the water. I'm going to help you one more time though. Guess we can't say that we haven't given you enough examples to try to mirror, because once you start looking at them, they all work together. But one mole on top, so I'm going down to my flow chart. I went from grams to moles. Now what am I doing? I'm going from moles to moles. My accent's totally gone. So there's one of these for every 4 of those. Right? I'm just going from one thing to the other. You're not going from multiple things. You're going from one beginning point to one ending point. That's it. And then 1 mole of water. You got 18 grams of water. Divide, multiply, multiply. I'll do this part for you. 81.8 grams of H2O. No, you said it was 75. Again, that's what actually was made. This is what should be created. So if I think about that now, where does that go? On the bottom or the top of my percent yield? The 81.8. Bottom. The 75 goes on the top. That's what actually was created. And just like anything else, like in this class, if you're getting a 90%, that's an A, that's good. Getting a 80%, that's a B. It's not as good, but it's still good. Percent yields are the same idea. The higher the percentage, the better the reaction, the more efficient it was. tell you now, industry does this a lot. Industry doesn't want 100%. Costs too much. They figure out the maximum yield to maximum profits. All right, wait, if we speed this up a little bit and get a couple mistakes or bad quality products off of it and we have to discard, are we making more money because we're pumping more of them out at a time? Well, that's a percent yield. How much are we making percentage-wise? They pay people a lot of money to figure out the maximum profit line on that. And then I would get 91.7%. All right. Again, one last time. This is always given to you, or this one. You always have to find out. All right. So last thing, and then we're going to have a little fun with these balloons, and we can talk about the rest of the week. This, I believe, is your first problem on your worksheet itself. It's only 6 problems. There aren't a lot. There's no back. So you're in good shape. How much magnesium? Okay, here we go. I'm back. How much magnesium oxide is produced from 25 grams of magnesium reacting with 40 grams of oxygen? If a reaction does not have coefficients, you always need to balance it. Always. If you see coefficients, you're good to go. So those have 2's. Organize my information. I got 25 grams, I got 40 grams, and it's asking for grams of MgO. If you don't organize your information and you don't do well on this, it's really hard to grade you, or this is too harsh, feel sorry for you, and the fact that you didn't do the most important part, which is starting off by organizing what numbers go to what. So, the minute I see this, just so you know as we go, if I see 2 values and they're on the same side of the period of the reaction, that's a limiting reactant problem. So now that's saying, like, how much am I going to make from each? So I'm going to get you started. What am I finding? MgO on the right. Both times. So work with someone else if you'd like. Let's see where we can get right now. This should give you some confidence. This is a little bit of a confidence builder. If we can get this, we are in a great position. So beautiful.
What is the gram? 44. Alright, if you're having problems, get you started. Put the molar mass on the bottom. I have a 2 in front of the Mg, 2 in front of the MgO. And then the other one is exactly the same at the ending, just a little bit different in the beginning. So you should be able to mirror that quite well. Right, and then the second half is exactly the same.
Buonasera, signorina, buonasera. It is time to say goodnight to Napoli. Though it's hard for us to whisper.
You have any choice you want. I'd suggest, depending on your space, you can either go side to side or above and below. It's usually easier to do above and below, but I understand some of us, the way we write, we don't have enough space, so you have to go left and right. Again, I need to have you see that this is the same at the ending, because I'm solving for the same thing. Then do not leave that problem until you box the correct answer. You are not adding them together. You are boxing the smallest answer. Very important. All right, so one other thing I want to point out, even if you're not done, look at number 6, please. It says something to the effect that this thing's going to react with excess H2. All right, if I tell you that you have excess oregano or excess basil, that's not dictating how many pizzas you're making, right? So, same idea here. How many T-charts do you think you have to make in number 6? 1. Why? Because the other one has told to us that it's excess. Even if I told you the number, you know, I say, hey, there's 400 grams of it. Doesn't matter. The minute it's excess, as we said before, you were labeling, if you had to label these, Mg is the limiting reactant, O2 is the excess. The excess one never creates the final answer because you have more of it than you should. It's going to not run out. The other one runs out first. And that's a really important concept. All right? Final thing. Please, I know you're working on it, but I want you to realize something. We are moving our mini quiz from tomorrow. That's going to be on this. Like, can you read a recipe? Like about a pizza pie. Or anything else. And do one limiting reactant problem. We're going to bump that to Wednesday. We're going to talk about limiting reactants and kind of review from today. And then we're going to talk about our rocket lab. And our rocket lab's pretty sweet. And I'll actually show you the reaction in the rocket lab right now. But I need you to understand that the rocket lab is not a rocket we get in. We will not have mushroom clouds coming off of it. If you're thinking of that stuff, the lab's going to be destroyed for you. Be like, oh, where? I brought a bag. I brought an overnight bag. Where are we going? Like we're shooting them off in the classroom, and they launch across the room, and we'll say how far they go. And the cool part is on Friday, maybe a little bit on Friday, you might be able to get to it. But you were trying to figure out the best combination for your fuel ratio. So we have oxygen and we have hydrogen. And it's pretty cool. You can do it in such a way that you will make a bang or a pop, and you do it right in your hand. Now this is a little bit more, but this is hydrogen. If I react it with oxygen, it makes water, which you're like, oh. That's not good. Never had this happen before. Come on. Come on.
Mr. Gosse, just hit it. Hey, Mr. Gosse, just hit it back there.
That is also a good idea.
Jesse.
I'm not as stealthy as I once was. Talk about lighter than air. All right, so what I was trying to say, I'm so glad that's all on tape. Oh boy. Making water doesn't sound that exciting until you actually hear it.
by shrapnel.
You don't want to do another one? Yeah. Jesse said.
Jesse's suing because
What I was afraid of is if it got too hot in that light bulb. That's what I was thinking about. That's why I'm like, this isn't good. So I was jumping like a weirdo. Let's turn off the lights this time.
There's a flame.
Then I'll sneak up and do it on stage.
Like you can see that on the light. Go up, like watch the thing. You can see the heat.
Oh, there's no candle on. It helps.
Blow it up. Mr. Newbar, this is what I ask all the time about explosions.
Way to ruin the moment! Happy March 9th, everybody! Alright, so, to finish up, we will be doing the rocket lab. You need your lab books. And what you're going to be doing is testing little pops. And they actually will pop. And they will make mini little explosions. Not quite that big. And the loudest pop, then you say, hey, that's my ratio for my rocket fuel. So then you'll figure out that ratio in your rocket. And then we actually put a grill lighter inside that creates a spark in the gas. And then, boom, it goes and flies. And we record how far you went. And you get multiple tries. So it should be a lot of fun. But have your lab books for sure. Try to have them Thursday. We might have time to write in them a little bit, but you will need them for surely Thursday night to have it ready for the lab. All right? So you have 9 minutes. The sheet is due tomorrow, so you have time. You can work with people. Oh, last thing. And I'm speaking for myself, but I'm sure Mr. Neubauer and Mr. Blackford have run into this. Grading, and actually 3 of you are in this class right now that I'm talking about. Grading labs. Interesting that conclusions are word for word the exact same. I was actually going to post them up. Those automatically, for me, I took off at least 5, if not 6. And if it continues, if we're just copying conclusions, the whole lab will be zeros. This conclusion, again, about 5 or 6 of my tour kids all had the exact same conclusion. And you got to realize, oh, I'll just let this one person. If they copy it down, all of a sudden 3 people copy from that person. Next thing you know, it's all going around. Doesn't matter whose it was. You all have the same. You cannot, oh, we work together. That is the worst excuse I've ever heard. You cannot have the exact same thought and idea worded the exact same words in 300 words, every one of them the same in the exact same word. That's called copy. So be very careful. We want to hear what you think. And if you're working with someone else, it's great. But just be very careful because it's starting to show up a lot. So get working on this. We will see you in class tomorrow.